So my name is Joe Silk. I'm one of the organizers of the fine-tuning project that we're running through Oxford University. My specialty is cosmology and dark matter and many of the big questions in the universe. And this is one of a series of discussions that we're having. And today, John Peacock is joining me, and I'll let John say a few words.
I'm John Peacock. I'm a cosmologist at the University of Edinburgh. The sort of things I work on are at the theory-observation interface. So I'm particularly interested in understanding the whole sequence of formation of structure in the universe, particularly using large galaxy surveys, mapping the large-scale distribution of matter, and trying to understand how that was built up by gravitation and other processes going back to very early times.
So John, I'd like to understand your views and how they might differ from mine on the questions of how you apply statistics to the sort of the real world that we both work with, data in cosmology, how we can verify theories or falsify theories. This is a continuing battle that we have in the field. So how do you stand on this?
I don't think it's a battle about principles, really. It's more about what you do in practice. And everyone understands at the root the whole idea of a statistical approach. You're measuring something with some degree of imprecision, and you want to know, given a set of data, where the truth lies. Now, I think the difficulty comes where the truth is something that you would think of as part of the background. Okay, so for example, let's say the gravitational constant, a number in the universe that specifies the strength of gravity. Does it make sense to talk about the probability of that having a particular value? You might reasonably say, well, the universe is as it is, G has some value. There might be a consequence of G that you could measure, let's say, the orbital period of a particular planet around a star, and so you might make observations over a limited range of signal to noise and say, well, I know this period to a certain range of precision. And people are used to that being something that's uncertain in that way. But the question is whether it makes sense to talk about the value of G, so part of the kind of background props of the whole play, having different values. And of course the Bayesian worldview is really quite radical, because it says you're allowed to use the same term, probability, that we apply to truly random things like coin tosses, to your belief, your state of knowledge about something. So it doesn't quite imply that something is uncertain. So it's a statement about you more than about the universe. And yet somehow we're able to use the same mathematical language to describe two actually rather different things.
So there are sort of two aspects to this. One is, adding more decimal points to some fundamental constant of nature. And people even disagree about what constitutes a discovery via some phenomenon that might be more than a decimal point. I'm thinking of dark matter, for example, where people go out and they find some indication in some experiment for a dark matter signal, and they talk about levels of significance. Mm-hmm. And if it's at a certain level of significance, they will publish a paper announcing a discovery. On the other hand, that's common for astronomers. It's also common in particle physics, but there's a fundamental difference in that in particle physics, one has a much higher standards of what constitutes discovery. And that's one of the aspects that makes our field very confusing. At what point do you say, aha, there is something new, mm-hmm. Maybe a new property of nature or a new value to some constant that you're searching for? Or at what point do you say, well, I don't really know, I haven't verified this?
Yes. Well, if there's any particle physicists listening, maybe they should shut their ears at the moment, because I think the way they approach it isn't rational. Look, normally in astronomy, if you have a signal that's there at the 3 sigma level, which in random trials is probability of one out of 1,000 outcomes, you would publish it and say there's an effect here. Now, the only reason is that going to be wrong? How could it be wrong? 2 ways. One is, well, maybe you wrote 1,000 papers looking for effects, and And so you're virtually guaranteed to find something just by chance. And that's been given a name in the particle physics language. It's an awful thing, the look elsewhere effect. So, for example, when you were trying to detect the Higgs, they could look for signal in certain mass channels. They didn't know which channel it was going to be in. So obviously looking in 100 different channels and looking for a 3 sigma excess is incorrect. But you should fold the number of different trials that you've undertaken into the probability, in my view. So the idea that you forget about the number of trials you've undertaken and just say, I look for 5 sigma in one because that's completely safe. You know, it works, but it's a slightly sloppy approach. You can do better.
There's another worry here. I mean, in my lifetime, I remember seeing what was a 10 sigma effect or more, 12 sigma. They were, at that point, discovering distortions in the microwave background radiation. These went away. So 3 sigma, 5 sigma, 10 sigma, there are other issues there, namely systematics.
Exactly, that's nothing to do with statistics then. I mean, no amount of formal statistical precision could insulate you against there being some effect in your apparatus that you didn't understand. You know, that's why we look for robustness. We look for, when we claim something really big like the universe is accelerating, you want to see that demonstrated by a number of lines of completely independent evidence.
So is this somewhere where Bayesian belief could help you? Because, you know, you could have an intuitive feeling, say, that a certain experiment might have systematics that we don't understand, have more confidence in that than another. And that would constitute a Bayesian approach. And would that give you a different evaluation of some result, for example?
Maybe, but it depends how you parameterize it. So, I mean, the great thing about the Bayesian approach is that once you lay down a framework for how you're going to approach a problem, so let's say we talk about the energy density of the vacuum. So is it a cosmological constant that's making the universe accelerate, or is it something with some equation of state that means the balance between pressure and energy density is different from a classical lambda? Well, that number, once you've decided I'm going to parameterize things that way, then you can try and pin down the variation in that parameter. So if you have 2 inconsistent experiments, you would have to have some kind of hypothesis about the kind of effect that could have caused them to be inconsistent. And then you try to marginalize over that, right? Allow that physical effect to vary, and then incorporate that into your uncertainty. But you can't do it without. This is the problem with the Bayesian approach, that you need to be quite prescriptive about the kind of model you have in mind. So sometimes I find myself more drawn to the kind of frequentist worldview, because you need to assume less.
So another example, and I'm not sure the answer here either, is if you are convinced, for example, that say that Einstein is wrong, and you want to explore some different type of gravity theory, a minority of people do that, a significant minority today. Others assume Einstein's theory and work on that basis. I mean, is there some way to, it would be interesting if there was some way to say, well, you know, you're likely with some probability to be wasting your time doing this or that. Is that a potential way of, you know, somehow using our prior knowledge to... I mean, that decision is important when you start giving out money and funding agencies.
Each one of us does that. Right? I mean, I'm not actually sure how much of your professional day you spend working on modified gravity, but for sure, if we could prove that Einstein's description of gravity was wrong at a classical level, that would be one of the biggest developments that either of us could imagine. So you might think, well, surely there's motivation to work on that. But from a Bayesian point of view, you say, well, what's the prior probability that Einstein's theory is simple, powerful, general, and already quite well tested, could be wrong against some much more complex alternative that just doesn't look very appealing when you see it written down. So you know, I think most people feel that there's a possibility that gravity is modified, but the kind of intrinsic odds are against it. And so you'd want to see, at least I'd want to see, pretty strong evidence, extremely strong evidence, before I'd start to become a believer. So the danger with this, of course, is if your prior belief in the theory is too strong, no amount of evidence can ever persuade you. And there's been historically in our subject great examples about this. I mean, there's still people out there who don't believe that there's a non-zero cosmological constant, even though the weight of evidence is as strong as just about for anything, because they have such an abhorrence. And I was one of these, actually. I was very much somebody who was reluctant to believe that the universe could have a non-zero lambda. And it took me a long time to come round to the fact that this is where the data were pointing. I don't know, was that true for you? I mean, when did you become a believer? Or were you an early adopter?
I merely followed the flow, I would say. As the majority switched, I went with them. I had no strong views at the beginning. Lambda was unpopular early on. I regard it as a minority view. But getting back to this rather subjective issue one has to deal with when you deal with theories that maybe in some sense unpopular or minority view, that there comes a point now where if you're in certain funding agencies, you're looking, for example, for projects that might be very high risk but also potentially very high gain. Mm-hmm. And so, for example, would you put working on modified gravity in that category? If so, then the people running these agencies would say, aha, maybe I should devote some funding to that direction. But if you decide that it really is completely something that'll go nowhere, or just is not sufficiently justified by the data that are out there, then you might not want to fund it. So how do you think one could address that dilemma?
Yes, well, look, if I was a funding agency, which thank the Lord I'm not, you can't do better than to give money to smart people. So if smart individuals are motivated to want to go in these slightly off-the-wall directions, then I think you should back them. So that partly it's a question for the individual as for the funding agency. I think rationally, you regard it as a bit like betting on maybe betting on the national lottery. Mm-hmm. Right? It doesn't hurt you to buy a £1 ticket as long as you have no strong expectation that you're going to pay for your mortgage as a result of winning. So I think personally, I'm happy to spend a fraction of my research time on things that are high win, high risk, high payoff. But I also want to do some bread and butter science that's guaranteed results, even if not necessarily going to win the Nobel Prize. Right. I think funding agencies have to do the same.
So how far off the wall could one go, though? I mean, clearly,
Well, you couldn't go much further than the multiverse.
Yes.
So I have a research grant at the moment which adheres exactly to that that template. Some fraction of it is directed at the multiverse, but a good fraction of the work is kind of more vanilla cosmology.
So do you think one can actually eventually test the multiverse in some sense? Or any aspect of it?
Yeah, I do. Obviously, you have to read the fine print, but it is. I mean, you can't talk about the multiverse because if we are in any sense part of an ensemble, then we don't really have a firm idea of what that ensemble has to be. There are a number of possibilities. So what you can do is you can formulate. I mean, I think the multiverse is no different to any other kind of science. You can formulate hypotheses, look at their predictions, and those predictions can be tested and falsified in some cases. So the only difference with the multiverse is that predictions are much less sharp or smaller in number than they are in other fields. But if the discrepancy is sufficiently marked, then that theory has been put to the test.
So here's where we might disagree then, because it seems to me that by definition, the multiverse is an ensemble of universes between which there is no communication possible whatsoever, given current physics. So I have a problem understanding how one can relate testing the multiverse theory to physics. Maybe you have a clean example of how one might do that.
Yeah, well, the test is statistical, so you're having to try to predict the probability distribution across some ensemble of. So I think to me this is where it's actually quite helpful to think about things in a frequentist rather than the Bayesian way. So somehow the idea of making, let's say, making many copies of our universe and making each one different in just one respect, and the dominant case you want to think about is lambda. So there's an interesting, simple model, which perhaps is unlikely to be a real multiverse, but you can postulate it and see what its consequences are. So make many copies of the universe that we live in, and imagine going back in time, at the time the microwave background was created, the vacuum energy was what, 1 part in a billion of the total density. So you can increase that by many powers of 10, and at that time they're all identical. Then run them forward, watch how structure develops in different ways within them. And the ones with more structure in are more likely to seed observers. So you can try to construct, as a function of the value of lambda you've injected, what the weighting towards numbers of observers is. And that gives you a posterior distribution for the value that the observer should see. Right? And then we compare that to the one number that we observe.
Sure. So that all sounds very nice.
So,
but the problem I have,
that I think is fine. It's restricted in its compass, but it's a worked example that shows you that in principle, then you can make this work like normal science.
Right. So here is a problem that I think has been expressed with the fundamentals behind that approach. And that is the multiverse, by definition, is an infinite or quasi-infinite series of universes. And there is no simple way to establish any set of measure that allows you to compute probabilities. It's been a problem that's been challenging the cosmologists who work on multiverse theory for a long time. I don't think there's a solution. So if you can't define probability functions, how can you possibly then end up with some robust strategy for probing the distribution of the cosmological constant, for example? Yeah.
Well, I'm not denying this is a serious question, but let me give you the answer that Stephen Weinberg gave to that, which I think I find persuading. The difficulty is calculating these priors. But one can presume that in the end there is some function. So, if there's an ensemble at work, there has to be a prior value of lambda. So the question is, what is this function? We don't know it. So that means, in a sense, the whole Bayesian framework fails at the first step. But Weinberg's argument was to say, well, but we're not actually interested in the whole function. The whole reason that, as you know, everybody in cosmology is so exercised about the vacuum energy is that the natural value of it should be many, many orders of magnitude larger than what we observe. So we're only actually interested empirically in the value of this prior at values very close to zero. And the whole puzzle is that there's nothing special about zero. The vacuum density could be hundreds of powers of 10 larger in the positive or the negative direction than the value we observe. And we just want this tiny little domain in the center. And if you simply say that zero is not a special point, which is the whole basis of the argument, because if we knew that zero was special, then we might think we're on the track to actually the direct physical explanation of the value of lambda. Then you only need this unknown function in an infinitesimal part of its domain, and therefore you can treat that as a constant. That was Weinberg's argument. Now, but it's very difficult to make that argument work when you let other physical parameters scan. Particularly curvature. If you wanted to try and make the same argument with curvature, you go completely wrong.
That's right, which one has to be, I think, rather cautious about the argument. In particular,
unfortunately, this is something of a special case, which shows how hard it is to make this framework work in full generality. If you take the string theory point of view that basically every aspect of physics is likely to vary in different members of an ensemble.
I'm curious about Weinberg's argument, even if you restrict yourself to the cosmological constant. I mean, he used the bound between zero and some small value on the grounds that if lambda was too large, one wouldn't make galaxies. But once you allow lambda to be negative, you can make galaxies even more easily.
No, exactly.
So doesn't that open the Pandora's box already? And
Do you know, I think the universe missed a trick here, because if you think it's equally likely the cosmological constant could have been positive or negative, it would have been so much sweeter to live in the case where it's negative.
Well, look, it's not because if you ask the string theorists, they began.
Yeah, they wanted that.
That was
yes,
negative.
Yes.
That's right. Yes.
But I mean, think how that develops. Such a universe always expands for a while and then recollapses, because the cosmological constant then, instead of accelerating things, decelerates. And moreover, when the universe is recollapsing, becoming denser, the formation of structure is more efficient than it is in the earlier phases. So almost all the formation of structure would happen after the universe has turned round. So if you lived in such a case, you'd be overwhelmingly likely to look at the sky and see all the galaxies coming towards you. Mm. And how we'd have ever made sense of that, I think is interesting to speculate how the history of the subject would have gone.
That's true, but
anyway, but to get back to the question, we don't see that, so why not? And the answer is that, of course, there's not much time between this kind of post-turnaround structure formation and the ultimate big crunch, when the whole thing goes to a singularity. Mm-hmm. So you have to allow. One of the difficulties, I think, about any of these anthropic arguments is that you find yourself being in danger of dragged away from physics towards biology, which, on many grounds, one doesn't want to do. But I think it's not too much to say that after a galaxy is formed, there's got to be a reasonable time lag before any sort of complex life is going to form. And if the cosmological constant is too large and negative, that remaining amount of time post-turnaround to the crunch is just too small. So I think it's that cuts things off. So to circumscribe the actually permissible values of lambda, you have to do it in very different arguments on the positive and the negative side. That's
true, but it does mean that when, it's been said that this argument pioneered by Weinberg predicted the value of lambda.
Well, he did predict it. He wrote it down.
That's true,
but in
fact, it doesn't seem to even to get the sign necessarily correct. If you generalize the argument, if you take it.
Yeah, he could have gone into more detail on the negative sign, but even understanding why it's not large and positive is that's a question that needs to be answered.
Absolutely, that's right. Yeah.
Although I don't know. Do you believe that just picking it apart? I mean, this argument works if you accept his idea that large lambda suppresses structure formation to the point there's no galaxies like the Milky Way. Mm-hmm. And to me, the open question is whether, in the end, enough of the gas might be processed into stars, even in galaxies of, say, 1,000th the mass of the Milky Way. Generally, the literature assumes not, and I think if you allow that possibility, then the testability doesn't work out so well, because lambda could have been very substantially bigger than it actually is.
I completely agree with you. Yeah.
Well, I'm a kind of agnostic.
Yes.
I'm quite a fan of this mode of thinking. A, because I'm impressed by the fact that Weinberg made a correct prediction, and B, because, well, if this isn't the way of explaining it, do we have an alternative?
Well, that's a whole other story. But at least there's so much uncertainty in galaxy formation and star formation, etc., that one does have a lot of freedom. And while the argument qualitatively sounds very good, I think it's hard to make it. I would think it's hard to make it quantitative, to get a precise prediction as to what lambda might be. So, qualitative stuff is fine. It may not really be hardcore physics. I don't know. It certainly is physics at some level, but. You mentioned curvature as something that's very hard to understand from arguments like this. Would you? How far off do you think one can go? How far wrong can one go with curvature predictions ab initio?
Well, okay. When I first started thinking about this, I was kind of puzzled historically that people didn't go through very much the same sort of argument that Weinberg did about lambda with curvature. Because curvature has, in many ways, a similar sort of effect. If the universe has below critical density, then after a while it expands in a way that's not decelerated at all. Gravity is effectively not important, and structure ceases to grow. Right? So if the universe is more heavily curved, then structure formation would freeze out at an earlier and earlier stage, and then there'd be no galaxies. And so, Bob Dickey in the 60s was musing about these sort of issues. And I don't know, and I didn't know at the time why they didn't just make the same argument, saying, well, curvature can be positive or negative, let's assume that there's a prior probability that's uniform near zero, and now calculate. And you would have concluded that you're overwhelmingly likely to be in a closed universe with positive curvature and so on. None of that was done. And from where we sit today, that's a good thing, because most people, when they think about an ensemble today, would say, well, it probably comes about in the context of inflation, where you're talking about an exponentially increasing background that at particular places nucleates bubbles of lower vacuum energy, which are the universes within which we sit today. And that tunneling process that produces those bubbles only produces universes of negative curvature. So the whole positive curvature is completely ruled out. And if you made a prior that didn't include that physics, then everything would be completely wrong at the start. So this is an example, it's a worrying example to me of how you need to know a lot about, more than you're ever likely to know about, the physics of what's generating the multiverse ensemble before you can do any Bayesian calculations with it.
So that implies that you'd want to have some reasonable proof that inflation might have occurred, and we're a long way from that still.
Well, that's right. There was a blissful moment in 2014 when it looked like primordial gravitational waves had been detected, and for an instant I was a complete convert. Whereas now I think I'm probably more sceptical about inflation than I am about the multiverse, which is kind of inconsistent, because in a way, if you want to think about the multiverse, it's helpful to have inflation as a convenient generator of these bubbles.
So it's been argued that because of the recent developments since that non-discovery, as the Planck satellite has improved its sensitivity on setting limits on inflation models, that now we're forced into a regime where I wouldn't say that inflation did not occur, but rather that if it did occur, it was incredibly complex. And it is these complex inflation models that are closer to the multiverse than the simpler ones that are now more or less ruled out would be. So maybe that encourages you towards the multiverse.
Do you think so? Because, I mean, one of the reasons I was excited is the very simplest inflation models, the ones that predict Lindy's original chaotic inflation, that predicted large gravitational waves. That's necessarily a generator of bubbles, yes. But not all models are. So, I mean, I don't know what the difference between a complex and a complicated and a simple inflation model is, because in the end, all we can observe are about two numbers. Right? If you accept the whole package of inflation, then the expansion of the universe at early times is affected by the value of a scalar field, a bit like the Higgs field, and all we know is something about the potential energy function that it's being driven to change by, but we only know the slope of that function, and maybe its curvature, and the whole rest of whatever landscape it's sitting in is unexplorable. And understood,
but it's the single field, the simple, which I mean the same was the being.
But you can always make a single field model work. The question is how
that's true.
How plausible it is.
That's true. So it's getting restrictive enough so that many of our colleagues are now talking about multiple field models, and these lead you to inherent problems. Not just that some of them would favour multiverse, type production, but at the same time they're also intrinsically highly non-Gaussian. That's another generic consequence, and that may well mean that it becomes even harder to do statistical calculations of initial conditions now than it was before. That's another worry, I think.
Yeah, well, I think we're in agreement. Inflation could do with some more
yes.
Observational constraints on it.